Hi, everyone. Welcome to our CS109 final project. So our group did mortality prediction using the National Health and Nutritional Examination Survey data. And so we are Rudra, Rosan, Albert, and Jeremy. And this is our project. So a little bit of background about what we want to do. We were obviously motivated by the mortality data. So we were focused on what factors increase the risk of someone dying and how important those factors are. And also, we also wanted to build a few models that would be able to predict your longevity. So as far as our detailed implementation plan, we carried out the four major steps of the data science process, which involved acquiring data, doing some exploratory data analysis and data processing, then doing data modeling, and then finally presenting our results. And so throughout the rest of this presentation, we'll cover each of these steps in more detail. So in the first step, we want to talk about the data that we obtained. So the data is from the National Health and Nutritional Examination Survey, and the data originally came on data tapes. However, this was then converted into a CSV format thanks to our wonderful TFs. And so this data has 42 columns with 41 of them being predictors and one of them being a response, with all of the predictors being medical information and data gathered between 1971 and 1975. And so overall, there were 14,407 observations, with each one of them having a response variable to go with it. So now, some of the response variables were negative, but this doesn't necessarily mean that someone lived a negative amount of years. Rather, the negative sign is an indicator that the subject was still alive at the end of the study or simply stopped participating in the study within some period. And so now we'll do some pre-processing on the data.
So we started our data pre-processing by one-hot encoding our categorical variables. Then during our EDA stage, we also found that data was not missing completely at random. This visualization shows how the missingness of predictors is correlated. Now, based on this, we decided to go with a multivariate imputation approach, which makes use of these underlying patterns by predicting the missing values using the rest of the data set, which is different from imputing the mean. As our baseline model, we chose multiple linear regression because it provides a good benchmark. Then we moved on to a single tree model and improved on that by using a random forest. Finally, we fit a neural network on our data. MSE was used to compare the performance of each model. Now, tree-based models and neural networks have the drawback of weak interpretability. We address this problem by computing SHAP values, which essentially capture how much a particular feature impacts the prediction.
So in order to express more of the complexity of our model, we wanted to use neural networks. And so we used the TensorFlow library to create neural networks that are feed forward with 3 layers. And we used the ReLU activation function, which provides the nonlinearities required to be more expressive. Then we trained our neural networks using the Atom optimizer, since research paper shows it has good performance, and it's especially optimized for large data sets and large numbers of predictors, which matches our use case. We also experimented with epoch and batch sizes to find a good fit that struck a right balance between the training speed as well as the model performance. Then we have one caveat though, and that's that neural networks are less interpretable than the simpler models we use because of the vast numbers of parameters in our models, since we have 3 layers with a large number of neurons in each. So we decided to use SHAP to get more interpretability. And as we can see in the SHAP diagram, age is a dominant predictor once again, followed by sodium and poverty index. But in this case, the SHAP values are more balanced. You can see for sodium and the other ones, they are a bit closer to how age does. And so now if we consider what is the most promising model we have, well, neural network performs the best in terms of the test MSE, but we want to look beyond that and consider interpretability for real world use. Since if we're giving this to doctors or life insurance companies, we believe that the decision tree model would be the best since it is more interpretable and it doesn't sacrifice much in terms of performance.
The top predictors across our models align with what's currently present in medical literature. Excess sodium increases blood pressure because it holds excess fluid in the body, and that creates an excess burden on the heart. This damages blood vessels and arteries and ultimately leads to higher risk of cardiovascular diseases and ultimately premature death. Surprisingly, we found that serum magnesium, the level of magnesium that's present in our blood, can also contribute to lower life expectancy. Higher levels of magnesium can lead to cardiovascular complications such as hypertension and neurological disorders, and it's usually attributed to alcohol disorders and gastrointestinal losses. Unsurprisingly, poverty and income are also correlated with life expectancy. This is because access to poor education, higher crime rates, poor nutrition, lack of healthcare, and poorer housing accumulates to a shorter life expectancy and ultimately a premature death sometimes. For future work, we would love to explore other types of neural networks, such as recurrent neural networks and convolutional neural networks, as they were the most promising model for our current rounds of testing and training. So also, we would also like to go forward with exploring the Cox proportional hazard model, because research showed that although it was less complex, it was considered a popular survival model because of its interpretability. Thank you for your time, and thank you for an amazing semester.